So in the last lecture, what we saw was the work done by the constant force, in which we had a constant motion, and we saw that how to write the work energy theorem when motion is constant. So today we are going to study something called work done by internal force on a system. So there are three types of, whenever we talk about the internal force, it means it will come as an action reaction pair. So if you apply force on me, then I will apply force on you. So there is always a pair of forces when we talk about system. And we would like to understand that how they work on a system. So we'll put this internal force into two categories. So we have something called the internal constant force. And then we have the okay. And then we have something called internal. The force is going to be internal, but it is not going to constrain the motion. So it's called non-constraint force. Now, under this category of constant force, we have three separate category, you can say. So this is what we have discussed in past also. So internal constant force. Constant means what something which restrict the relative motion. We call constant. So we know that the normal force will restrict the relative motion in the normal direction to the surface, and the static force of friction will oppose the relative motion parallel to the surface, and tension if it is internal, then it will kind of do not let the string to be loose. Okay, so we cannot snap, slack the rope or string. the rope or the string will remain always taut. So keeping it taut is kind of constraint. Okay. And whenever there is a constant, the motion will have a relationship, as we have discussed. That a constant motion means the velocity vector, or you can say displacement, will have some dependency on each other. So they cannot, like, we cannot move freely. If you move, then other will have to move in certain way. So constant means when the motion is dependent, we call it constant. When the motion is not dependent, you can move the way you want, then it is called non-constant force. So under the category of constant force, we have three forces. So we have static friction. We have normal reaction. And we have tension. And what you are supposed to remember that work done by static friction, normal reaction, and tension on a system, on a system is always zero. So constant force cannot work on a system. So what they do is they do positive work on one and negative on the other. The sum is always zero. So what I can write in general is work done by internal constant force on a system is always zero. So no need to even think about. I mean, you can create some example and you can explain. It's very easy. So, for example, if I talk about two blocks, and if both are moving, because there is a static friction, so it means both cannot slip. So, if this will move x, this will also move x, isn't it? Because they're not moving relatively, it means they have to, I mean, the displacement suffered by each object will be similar. And in case of friction, if friction is acting on the upper block towards the right, then it will act on the lower block towards the left. Therefore, it will do positive work on the one and negative on the other. The system will always get nothing. So as a fact, you should remember that internal constant force never work on system. Of course, it will do work individually, but not on the system. I hope this is clear.
Yes, sir.
Now, under the category of non-constant force, so you will also come across a situation. I'll just draw the situation as well. I'll just quickly draw it. So friction force on the block, if acting forward, it will act on the lower block leftward. So you can see the friction work is positive for upper block and negative for lower block. Sum is zero. Similarly, if you talk about the tension as an internal force, and if the system goes right, so T will do the positive work on the lower, I mean, so the left block, and negative on the right block. So you can see again sum is zero. And if you talk about the normal, and imagine this is in an elevator. So the normal will act on the upper block like this, and the same normal will act. And if the displacement is same in the vertical direction, so you can see the n will do positive work on the upper block, and the same n will do negative work on the lower block. So again, the sum is zero. So that's why we say that internal force never do work on a system. Yeah, they do work on individual parts of system, but not as a whole. So it will do some positive work and some negative work. The whole idea is when we are solving the question of work, energy, and theory, then we should not, in fact, need to think about writing the work done of internal forces if we are writing the work energy theorem for the entire system as a whole. In case of non-constant force, you will come across a kinetic friction. That's very interesting example. because kinetic will let you have relative motion, so you can displace, so therefore you will not travel by the same value. So if Ft is acting forward and Ft is acting backward on a system, then both will not move by same value. So if there is a relative displacement, because in kinetic friction, a relative motion is there, right? So because of the relative displacement, there is some work. It's not zero, it's non-zero. So I'll come to that exactly how much is that. And then the last is called the internal spring force. So if I have a two mass connected with a spring, so spring force will act on both, and of course on a system it is zero. So either it will pull or it will push. We don't know whether it is elongated or compressed. But the only thing is clear that on a system it will do zero work. Okay. And therefore, okay, sorry, it will not do the zero, no zero work. In this case, because the spring can be deformed, it can move. Therefore, internal force in this case can do some work. Okay. And when spring will come into picture, when they will do their work, they can also store energy. So they have the ability to store energy. So they work and they capture energy from the system from which they are connected to, and it can store it. So whenever it is storing, it can give you back if the spring goes back to the original length. So this is how internal force can do work. So they will ask question: is it possible to do the? Is it possible for the internal force to do the work? The answer is yes. Internal force can do work. So work done by internal non-constant force on a system is non-zero. So work done by internal force. So when I say internal force, then internal force can do work, cannot do work, depending on whether it is constant in nature or it is non-constant in nature. So this is the idea which one should be aware of. I'll go to a really nice example of kinetic friction because that's very important for you to learn. So I'm putting as a separate topic work done by uh, on a system. So this is a very famous example you come across in different chapter also. But here we are going to solve using the our rudimentary approach of laws of motion. But as you grow in this chapter, we have a chapter called center of mass and conservation of momentum. So there we can solve with ease. Okay, so now this is a situation. What we are going to consider is, let's say the bottom is smooth, okay, and the blocks are having friction. So we have, let's say mu is the friction coefficient between the block and the plank. Okay. Now what I do is I give some velocity v naught. Okay. And imagine the plank is very large, I mean, very long, you can say, infinitely long. So it means the block will never come off the plank. It will always remain on the plank no matter what. Okay. And you impart some velocity v naught to the block, what will happen? So the first thing that will happen is, because of friction force, plank will accelerate towards right, correct? So what will be the direction of friction force on the block? Any guess? If you do the ABD, what is the direction of friction force on the block, the small block?
Towards the left.
Excellent. So friction force will act like this. Which friction will act? Static or kinetic?
Kinetic.
And as per the third law, the same friction will act on the plank in which direction?
Towards the right.
And plank is having no velocity, but the block is having velocity v naught. So which one will accelerate and which one will decelerate? So what is the acceleration of the small mass? The value only. I mean, of course, it is retardation. So what is the value? How to find acceleration? Newton's law. Tell me. What is the acceleration? How you find the acceleration? A equals to? Hello. Siddhant, are you listening?
Yes, sir. A is equal to force by M, net force by M.
No, so what is the net force? In the direction of motion, what is the net force? Because if you look at the other force, it is normal direction. And gravity, right?
Yes, sir. So negative Fk.
And the same normal will act like this on the plank. Another and then mg. So in the direction of motion, what are the forces? Only Fk, right?
Friction. Yes, sir.
So what is the acceleration?
Negative Fk M. Fk by M.
And what is Fk by definition?
Mu M.
And what is n here?
Mg.
So what you're getting is mu g, right?
Yes, sir.
But in the same way, if you try to find the acceleration of the capital M, it is not having any velocity in the very beginning. So what will happen? It will accelerate. So what is the acceleration? What is the acceleration? Tell me.
Mu G.
A will be? No,
Mu
what is
G.
A? No. How you write the acceleration? Force upon mass, right?
Like that. Yes, sir. Fk by M. Capital M.
It's such a simple thing. Why it is so difficult? It is force upon mass, but force is how much? And we have seen that this n is actually small mg, not capital mg, right?
So
So you can see that the acceleration is having different value. They are not same, right? Do you realize this?
yes, sir.
So now, if I draw the graph with velocity and time, so what will happen? Velocity of the block will start decreasing. So as time will progress, velocity will decrease, yes or no?
Yes, sir.
So this is going to be graph something like this. Let's say it is keep on decreasing. Maybe I can keep it like this. But what about the velocity of the plank? It will start growing.
Yes, sir.
And it is having less acceleration than the magnitude of retardation. So you can see the graph of VT graph of the plank and the block. These are different, right? And then you realize that at one particular point, both will become same, isn't it? And now this is the actually point of interest. What will happen if both are same? Do you realize what will happen? So they will settle on a common velocity, isn't it? Okay. And what does it mean is the relative motion will cease actually. When block and plank will have same velocity, then there is no relative motion and the suddenly friction will vanish. And then what will happen afterwards? Both will continue to move with the same velocity because of inertia. And they will not rub each other. There is no relative motion. So what does it mean? It means after some time, both will be moving together with same velocity, isn't it? Hello, hello.
Yes, sir.
Now, this is the biggest realization that we need to have. But when this will happen, the block will be on the left side or somewhere on the right.
Somewhere on the right.
So plank has moved a lot distance. But when they start moving together with same velocity, in the meantime, the block will travel some relative displacement. It will have some relative displacement. So who has traveled more, the plank or the block? Tell me. Who has
The
traveled
block.
more? The block. So the way of writing is this. So work done by kinetic friction on a block is, imagine let plank has traveled x. So if plank has traveled x, then how much block has traveled? Traveled x till block and plank attains.
So the block has traveled x, no?
Block has no, plank has traveled x. How much block has traveled? If plank will travel x, then block will travel x plus x relative.
Yes, sir. Got it.
So what is the work done by friction on block till that time, till they attain the common velocity? So you can see the force acting on the block is left and displacement is on the right. So what is the work done? What we can add the work? Minus Fk because it's negative. and displacement is x plus x relative. Do you realize this?
Yes, sir.
And what is the work done by same friction on the plank? Now, because plank has traveled only x and force is acting towards the right, so we can act as plus. Do you realize something? Maybe. You can realize one thing, that the negative work by the friction is more than the positive work by the friction, isn't it? So friction
Yes,
will do more of negative and less of positive.
positive.
So it is like if you give a small kid one glass of water, and if you tell, okay, let's say you are very young, very small, you go to kitchen, your mama gives you a glass full of water, and there is a guest in your house, so your mama says that to go and give it to your uncle or your aunt or whatever. So while taking the water, you will spill out a lot, isn't it? As a kid. Do you realize what I'm saying?
Yes, sir.
Which means the water is getting transferred, but there is a wastage also. And exactly this is what kinetic friction does. It will help in transferring the energy. So you can see that it is taking more energy from the upper block, but it is giving less energy to the lower block. And therefore, in the due process, some energy is getting lost, or we said dissipated. Or in physics, whenever there is a friction involved, and the loss of friction is attributed to the heat production. So we say that there is a heat generation in the due process of transfer. So that is why when you rub your palm against each other, okay, then you see it gets hotter, right? Because in the due process, a lot of energy is also getting wasted or dissipated, and the heat is a way of saying that the energy lost by any frictional force will appear as heat energy. So this is how we kind of, interpret the heat in case of frictional work. So sometimes they will ask you how much heat is produced. So the loss of, whatever you have lost during a transfer is your heat. So by the way, our question was, what is the work done by friction on a system? So work done by friction on a system, you have to add both the answers. So you have to just add 1 and 2. So if you add, what we get is, what you will get? Tell me.
Minus FK x relative.
Which means the work done by kinetic friction on a system does not depend on the actual motion, but it depends on the relative motion. How much they move relatively. Okay. And the same relative motion was not happening in case of static friction, but now it is happening. And therefore, you should remember that amount of heat generation equals to, so here negative work means energy is lost. Okay. So friction will dissipate the energy, because friction will do the negative work, which means it will take the energy, but it is having no mechanism to store energy. And fortunately in spring, when spring will do the negative work, it will not waste, it will store. That is the basic difference between the work done by spring and work done by kinetic friction. So amount of heat generation in the due process will be equals to Fk into x relative, the value. Let's take the modulus. So whatever is the modulus is called the heat generation, which we represent by delta H. Some author uses the symbol capital Q for the same. So you may be asked, or you will be asked, in fact, you are going to be asked in the JEE Advanced, of course, in other examinations also, what is the Q value, the heat generation value. And what you are supposed to do is just write Fk into x relative. Now, this question generally we attempt in chapter of collision or conservation of momentum. But here we have the better idea. We can see from scratch how things are happening. Okay. So it is very interesting. We will come across this interesting idea. So let's try to understand. Uh, let's try to calculate, not understand. Let's try to calculate both things. What is X relative and what is common velocity? Okay. So how to understand, how to find the common velocity, how we can do this? So we have what? We have formula, right? We know kinematics because you know the expression. So using kinematics, we can say for block, the V kinetic is V not minus mu gt. Am I right?
Yes, sir.
V equals to U plus AT because it's a retardation, so it's minus. And let's say time after time t, velocity becomes V. But for Planck, the V is 0 plus mu g small m by capital M into T. Am I right?
Yes, sir.
And because both are same thing, so we can equate. So you can see that we are using the kinematics also, laws of motion also. Using 1 and 2, we can say V naught minus mu gt is same as mu g m by m into T. In fact, this will give you the time after which this event will happen. After what time they are going to have same velocity. So in different chapter, the same question can be solved in different manner, but this is the first way that one should know. So the time after which this will happen is if you look at the denominator, it is basically the A relative. So basically A relative here will be in the frame of the Planck. What is A relative? So acceleration of M with respect to capital M is how much? It is mu g plus mu g m by n, isn't it? With minus m. You know why? Because Planck is accepting right and block is accepting left. So the relative is sum of the two, right? Do you realize this? So if I fix the Planck, if I only consider the block, the problem can be solved very easily. So if you take this as a frame, then what is the retardation of M? It is A relative, right? This much value.
Yes, sir.
And eventually it will come to rest after traveling how much? X relative. Correct? The V is 0. So you could have written
Yes, sir.
directly that V equals to U plus AT. So 0 equals to U minus mu G into 1 plus M by M. And still you would have got the answer. And this way of writing will also help in finding the X relative. So for X relative, what you can do? You can add again kinematical. Which kinematical equation we should use to get the X relative? First, second, third. You know the initial velocity, you know the final velocity, correct?
So if we can use the third one.
Third way. So V relative square equals to U relative square plus 2A relative into X relative. That's it. This is 0 because when you move together, then it is 0 because when you both will have the same velocity, it means it is at rest. Relatively. Okay. And this is and this is so you can get the x relative length is. Okay. And how to find the v, or do we got v? Yeah, we got v because we know the answer of v naught is this much. And what is v actually? V is mu g. So how to get v naught and v relation? You simply divide the two, right? So 4 divided by 3. But what we are going to get? V by v naught equals to? You can see something interesting. Mu g t will get cancelled, right? And this principle is called conservation of momentum. So we could have done this directly by conserving the momentum, but because momentum is a separate factor which we study, so here we try to solve by the very crude method, like something which is very fundamental. And if you can learn through this method, then even any difficult or any advanced method will be very easy for you to realize things, why things are happening the way it is happening. So we should have this understanding. So there are many ways of thinking. So using work and theorem on system, we know that on a system, the only force acting is internal frictional force, and there are no force acting on the system in the direction of motion. So we can say work done with all force equals to change in kinetic energy of system. And we know all force is only friction force. And this is, we know the answer. It is Fk into X relative. And delta K we can write as final minus initial. So final, we know that both will move together. And initially is only one is moving. And Fk is, we know the answer, it's mu mg. And then we have m plus m. So once you know the v value, you can get the x relative from this formula as well. So these are the ways of writing, and we know how to find a v actually. So the v is slightly difficult job, but you can get. And using v equals to mv naught by m plus m, you may substitute. And these things you need to practice, on your own, sitting at home. You have to spend few hours actually realizing this entire uh, set of events, like what is happening in these questions. Only when you realize you can use it in future, but Otherwise, your struggle will be on. And the same thing in the chapter of what we call collision center mass. We can solve in one line, or in fact mentally, because we know the derivations as a formula. So we can write as and you can take I think we can take here mv not is common. So we get m by. So this will give you minus m capital M by. And you can see the x relative is v not is by 2 mu g. Again is yeah. Same answer you can see.
Yes.
You can also write as mu square by 2 mu g. So there are many ways of solving. There is a third way also, and then fourth method also. It is about, do you realize the work energy theorem? Do you understand this? And how much you understand this? Okay, so in the work energy power chapter, uh, it takes time to realize things. It takes time to understand energy and how someone is giving energy, someone is taking energy. So if you understand the energy flow, you can write the mathematical equation which is, and then you can share. So as you study the conservation of momentum, then this question becomes pretty easy problem. It's not at all difficult problem. The common velocity we can get using the common velocity. We can conserve linear momentum of system, which means if you look at the momentum point of view, what was the momentum of the system? So it was only mv naught, right?
Yes.
And when they move together, then what is the momentum system? And why we are conserving? Because the frictional force is internal, and internal force never affects the momentum of system. So that's very interesting, that internal force can affect energy, but internal force cannot affect the momentum. It's very strange, but it's very true. So as of now, it will be counterintuitive, but in future you will come to know, okay, yeah, this is. So the same question you can solve in just like mentally one line if you know something more. And then you can substitute and get the answer. And then again in later future, which you will see later on. We have a direct relation method. So method will be like the kinetic energy of system in CM frame, I mean, whatever it is, just ignore it, is equals to loss energy due to the external internal. And then you can write directly as in this, there's a formula. This is half mu u relative whole square equals to fk x relative, and then the mu is called reduced mass, if you remember, which is product of mass and summation of mass. And the u relative is v naught square, fk is mu mg. And you can see that your answer is done in just this much line. So as you grow old in this business of solving question, you will come across variety of methods, tricks which can solve the same question which you took almost one page to solve in one line. So there are a lot of things which will come to in future. So then again, we have the impulse momentum theorem, which we again use to solve the question. So the whole idea is in mechanics, we don't have only one way to approach. Like whatever you know, if you know some certain things in mechanics, let's say you know kinematics, you understand law of motion, you understand friction, circular motion. Make sure that whatever you know, you can solve by your own known method. Like if you can solve through the kinematics, solve it. So keep on writing, keep on solving, keep on writing, keep on solving. You have to struggle a bit and then you can get the answer. So these are the ideas which one should be aware of. And with these ideas, you can solve question with ease. So this question was not meant for just solving. It was meant for actually exploring a variety of technique that we employ in solving question. How we can apply the laws of motion, friction, work energy theorem, all in tandem. So you understand one method, then you think of other method, then think of other method, think of other, and grow yourself in terms of thinking. So you can become a really good thinker and you can solve. So let's say I got the time. In fact, I can get the answer from T itself. So maybe I can use the method for so we know V equals to V naught minus mu GT and V equals to mu G M by M into T. So the idea is I can get T and I can simply substitute there. So the T, if you substitute mu GT is capital MV by small and then substitute here. So V becomes how much? V naught minus. And then you can rearrange. And then V equals to. So this is what we did actually. And because we know T, we can also find the X relative. So we have done, we can use UT plus half it is in relative form, you can get that. So you can use the T, and this is V naught into T. T is, we can see T, what is T. And the A relative is mu G1 plus. And then you can substitute T. So I will leave rest up to you to explore, to analyze, spend time. You have to spend a lot of time, maybe hours, before you actually realize all this stuff. But once you realize, you will find yourself in a very better position to answer even very challenging questions. So that is the benefit of the same. I'll go to the next idea, the next concept. So internal force we are done with. So the next idea is called actually now we would like to explore the spring force in general. So we have to do something called work done by so we know the formula work done equals to F dot delta or we write Fs cos theta. So tell me guys, this formula is only true for which kind of force? So this is true for forces which are constant in nature. So constant means they have not only constant magnitude but also constant direction. So you can say for a unidirectional constant force, a force which is constant in magnitude and direction both. This relation is true. So if a force, even though constant in magnitude, but changing the direction all the time, will term as variable force. Okay. So only so now I have named it constant force vector, which means it is not only constant in magnitude but also in direction. So as a vector, it is constant, not as a number. I hope this is clear what I'm saying.
Yes, sir.
Okay. So if this is the case, then how we are going to solve question of a variable force? If a force is variable, then what is the way of solving? Let me put a heading, new heading. Work done by variable force in one dimension. Okay. Imagine we have a block acted upon by a constant force. Okay. So this is your constant force acting on the block. So the direction is always towards right. But imagine it may be time dependent, it may be position dependent. So F is a function. It could be function of time, it could be function of displacement, it could be function of velocity. So you can come across questions in which the dependency can be written in multiple ways. Okay. So there are three types of dependency will come across: time, displacement, and velocity. There is no fourth dependence that you will come across. So the problem is, if something is variable, we cannot apply the above formula. So then what we can do? So what we do is we never try to solve for big values of displacement or time or big change in velocity. What we do is we do it for the small range, which means I will solve the question when you are at some in general position X and you only move by dx. If you do so, in that small displacement, can we treat the force value almost same?
Yes, sir.
So this is called elementary work, a work for very small displacement. We call elementary work. So in case of variable force, we define elementary work and then we try to add such elementary work. So it's like you have to find the elementary work and keep on adding, which will translate into integration. Okay. So you have to find each work in the elementary displacement. Then once you keep on doing that elementary displacement, and if you keep on finding the work for each elementary value, and then add up to all values, and if it is a continuous function, that will translate into something called integration. So what we do is we define elementary work. And we write dW. So we never think about the big displacement. We talk about what will happen if I go from here to here. So we try to understand what will happen. And from there, we try to understand the answer. So dW of F we can write as F into dx. Now, why this is so? Because the F is not a variable when the displacement is very small. So we are using the definition above definition. But instead of writing the full work, we are writing the elementary work. Because for elementary displacement, every force can be treated as constant force. Is this clear?
Yes.
So in order to get the net force, because that is what we are looking for, we have to add up. And therefore the integration sign will come into picture. Here F is not a constant, F is a variable. F may be constant. So this integration method is true for everyone, true for constant, variable, or whatever. But if it is variable, then the only way is integration. If it is constant, then we have two ways. You can do the formula or the integration. Is this clear? So imagine if you have a block of mass F, and if a force is acting equals to ax plus bx square, then find the work done in taking the block from x equals to 1 to. Okay. So what is the work done definition? And force is one dimension fx. So what is what definition? Integration of fx dx, the force in the x. And the answer is what? Ax square as ax plus. And x will go from 1 to 2. So the range will be the limits of integration. And I hope you can solve. So what we do is we put the upper limit first, right? So 2
Yes,
to
sir.
the 4, so 2 plus 8 by 2 minus lower limit, which is a by 2. So it turns out to be how much? 3a by 2. And 8 minus 1 is 6 or 7. So this clear? Is this correct?
Yes, sir.
So you can see that if it is one dimension, just you need to integrate and get the answer. What about the 2 dimension? So for 2D or 3D, you can just simply extend this definition. You write fx dx plus fy dy, and then put the limit respectively. Okay, so I will give you the example. Let's say a force is written as x square I cap plus 2y j cap plus z k cap, and a particle goes from A to B, and the coordinates are shown to you. Fine. Work done by force F. Tell me the answer. Chalo, do it. So you can clearly see the limit, right? X will go from 1 to 2, y is 0 to -1, and z 2 to 3, right?
Yes. So 2 minutes. Sir, is the answer 13/3?
Yeah, let me just check. So it is x cube by 3. Okay, I'm just doing the, let me do this. 2y dy plus z dz 1 to 2 and 2 to 3. So x cube by 3. Then y square plus z square. So 8 by 3. Nine by 2 minus 4. Correct? So 7 by 3. 5 by 2, right? Yeah. How much? 14, 6, 15. So this is what you should get. So where made a mistake?
Yes, sir, found my mistakes.
So it is very easy. Now, sometimes you need to realize something like okay. So imagine there is some random path given to you. Sometimes questions like this will also come. And this is the x-axis. A force which is always acting. So it is a variable force, but it is always acting this way. So it is Fx, but it is always acting like this. But the particle moves on this random path. So how you are going to deal with question like this when they show you something like a graph like this? So your displacement is along this path, and you can see the path is changing randomly. So it means, and force is also variable. So we cannot think of constant force, but we think of variable force. So this is the variable force. So we have to only think of elementary work. So how we do is we move elementary. That's it. So you go from here to here. You can call it ds, and you can call this angle theta. So let's this call fsx. What is the work done here? dw is how much? What is dw?
F cos theta ds.
F cos theta ds. Very good. So sometime you may be wondering that how we can make use of this concept. And you will realize that the ds, if you zoom the ds part, you can make a right angle triangle. This is theta. This is dx, this is dy. And you can realize something. What is dx? And therefore, this will actually become f dx. So actually, you have to only integrate in x, no matter what is the path given to you. So this will be like confusing at first go, but it is easy. And then to get the network, you have to just integrate. And because f is given as a function of x, so you can get the answer with ease. So this kind of question is also will be part of your journey. So in case of a very, let's say, if I want to just derive the formula which I wrote earlier, if you have a random path and if the force is also acting in random direction, these are the ways of thinking of derivation. And let's say this is the ds, this is theta. So you definitely write to work as f ds cos theta, right? Or f cos theta ds, isn't it?
Yes.
Now you may write f cos theta ds. And this is exactly f dot ds, correct? So I just took a random path and I have shown you. So I'll prove it for 2 dimensions. And then if we can write it, because it's a vector, we can write as fx I k plus fy. And ds is also slant, so we can write ds as dx I k plus dy j k. And then because of the dot nature, we know the I will go with I, j will go with j, so we'll left with fx and dx plus fy dy. I can see this is the dw. That's what the network done is going to be integration, and therefore this is what you get. Okay. So under this category, there is a very famous problem which one should be aware of. I mean, of course, you won't get at first go, but you should be aware of this problem. And you will come across this problem very often in physics. And the question is, if f is given by the formula y I cap plus x j cap, and if a particle goes from 1 to 2, 3, 4, what is the work done by the force? So try to solve or think about it, then I'll show. You can take some 3-4 minutes. Okay. Do it. So now, okay, let me solve this. So what is fx here? Tell me.
Y.
The fx here is y actually. How we find fx? The coefficient of I is called fx. So fx need not to be x. It can be anything. So the integration is fx dx plus y dx. Now there is a problem. We cannot integrate y with respect to x and vice versa. So this you cannot do. So there is a trick here, which comes from the chapter of differential equation. You may write like y dx and x dy together. Yeah, you can write like this. And this entire term in the bracket, we can rewrite as dxy. And d of something is something when you integrate. So the answer is actually xy. This is the answer for this question. And the limit will be 1, 2, 2. So put upper limit 3 for x, 4 for y, which is 12 minus 2. So now the question is, how sir you got this relation? So it is very simple. You start with the reverse process. What is, let's call z equals to xy. So what is dz by dx? So use the product rule. X dy by dx plus y into. And you can clearly see that dz by dx turns out to be, which we can rewrite as dz equals to how much? Multiply the dx both sides. And what was z actually? So this relation you must understand or remember. This will also come in electrostatics in class 12, sometime gravitation. So be it any chapter, if force is written this way, you should know how to do the integration. And x dy plus y dx is always dxy. I hope you will remember this.
Yes.
So there is another category of work done by variable force, which you will come across very often. And if you move on a curvy linear path, a track like this, and if the friction is kinetic, if it is kinetic friction, the property of kinetic friction is it always act opposite to the instantaneous velocity vector. What does it mean? At this point, your velocity is this way, and if you're rubbing the surface, your friction will be like act like this. But if you come here, friction will change the direction like this. So the nature of kinetic friction is that it only opposes the relative motion, and because motion is represented by the velocity vector, so it is always opposite of the velocity vector, no matter where you are. So what you realize from this example is that this kinetic friction is a kind of tangential force. It is always tangent to the path, isn't it? It is always tangent to the path. So this is something you should be aware of. I'll just remove this. And this will be our next concept. Work done by constant tangential force. Now, tangential force can be variable and can be constant. So if we have a path and if a force is always tangential and fixed in value, so it could be, let's say, tangential force acting like this. And because the path is changing the shape with zigzag, so we have to talk about the elementary work. So if you move from here to here, ds, what is the work done by tangential force? What is the elementary work by tangential force? So elementary work is how much? F tangential ds, right?
Yes, sir.
So what is the total work done by the tangential force? So we need to integrate and this turns out to be how much? Now I said that Ft is constant. So I can take it out of integration. And if you add ds everywhere, what will you get? What is the sum of ds? If you keep on adding all the ds, what will you get? No idea.
Sir, S.
You get the length of path.
Yes.
Right. So the very famous example of this is so actually this entire concept to be actually study only for this particular problem. So when we have a path like this, so we'll start with the circular path. So you have a circular path of a radius r, and a block is taken around the circle and it is horizontal circle. What you're looking is the top view so that you can see it clearly. So at any instant, if your velocity is like this, what will be the direction of friction? Exactly opposite, right?
Yes, sir.
And the value of friction will be mu into n, which is mu mg. Simple mu k. So if you go from here to here, so work done by kinetic friction from A to B will be how much? So because it is tangential, it is always opposite. So we have to think of only length of path. So we can write minus mu mg. Why minus mu mg? Because it's opposite of the displacement, elementary displacement, right? For every elementary displacement, it is opposite. Am I right? And the length of path is how much? R theta. Arc length.
Yes, sir.
Understood? So your answer will be So again, this is very important answer that one should know. No need to think much. So whenever you're trying to write the work in theorem for an object moving on a path where the force is friction force is kinetic friction and it is tangential. So no matter what path you choose, even if you come back to the same point, you will travel 2 pi r. If you make 2 revolutions, then 4 pi r. Because length of the path traversed. So if you traverse the same path again and again, the length will keep on adding, right? Why?
Increase. Yes.
Because see, even if you go in the same path again and again, the friction will always maintain this nature that it will always be opposite of displacement, right? Is this clear what I'm saying?
Yes, sir.
So a very famous question based on this, which you will come across very often, and it is also called the most challenging problem of SC Verma. It is also in Irodov. So let me first give you a simple example. If a block is kept on a rough horizontal surface, if block is kept on a rough horizontal surface, and it goes from A to B and then B to A. So what is the work done by kinetic friction in A to B to A? What will be the answer? What will be the answer?
So 0.
No. When you go towards the right, friction will act left. But when you go left, friction will act right.
Oh, so it will add up. Okay.
Yeah. See, it is tangential force. It is constant tangential force with the nature is preserved. So it is always acting in the same fashion. So it is always opposite of the displacement. So when you're going right, the friction is like left.
Fine,
But
sir.
when you're
Got it.
going left, so no matter how you try to travel, friction will always do the negative work, isn't it? So in a round trip journey, it is zero, non-zero. It is non-zero. Do you realize this?
Yes, sir.
So in fact, it will add up, which is actually mu mg L minus 2 times. So your answer is actually minus 2 mu mg. Is this clear?
Yes, sir.
Now, if I talk about the similar thing in case of gravity, let's say a block of mass m, it goes from here to here, A to B, and comes back. And my force is gravity. So when you go up, the work done by gravity is positive or negative?
Negative.
So the answer is minus mgh.
Yes, sir.
But while coming down, the work done is positive or negative?
Positive.
So in a round trip journey, the answer is
0.
so work done by gravity in a round trip is always now the force of gravity and the force of friction are said to be 2 different types of force in nature. So the force whose work done does not depend on the path, or whose work done is always 0 in a round trip, we call conservative force. But the force whose dependency is on the path. It means the way you travel will decide the answer of work. If the path is really important, then such force is called non-conservative force in physics. So you will come across a variety of forces. In fact, in this chapter, just two, but in the entire physics, you'll come across three forces, four forces, whose work in a round trip journey is zero. Okay. And not just zero, it is also path independent. So we have certain forces which do not, I mean, for those forces, we need not to check the path. We just need to check the beginning and the end, and from there we can discuss, okay, what is the answer. But there are some forces where path becomes really important, and we should be careful about the path which they took, okay, in order to calculate the work. So always remember, whenever it is kinetic friction, because see, you're not supposed to be very, this chapter is not very complex. We have certain fixed thing. Not there are not too many surprises, to be very honest. So work done by kinetic is something unique. That's why, see, I have been discussing kinetic a lot, you can see. So I discussed kinetic in the two block problem, the block and the Planck problem. I'm discussing the kinetic friction here as well. So kinetic friction is something which will give you some trouble, but rest of the force will be really nice on you. So in this chapter, the only non-conservative force which you will come across is this kinetic friction, and other forces you will come across will be conservative mostly. So conservative forces are category of force whose work is path independent. So no matter how you reach at a point, what really matters is where you started and where you ended. So when the point matters, not the path which you choose to be there, we call conservative. When path matters, not the initial and final point, then we call non-conservative. So what matters will decide its name. And in fact, we will study in the energy part, but as of now, we are thinking in terms of work. Okay. So tangential force is clear.
Yes, sir.
So let's say if I have a block which and let's say this is a quarter arc. So you have a block which you throw. This is L1, this is R, this is L2. Okay. And imagine that the force applied, so it is in the horizontal plane, and the force which is acting on this is F always. Let's say F is someone is pressing against the wall, and now it travels from the point A to point B under the action of same applied perpendicular force. And this entire setup is in the horizontal plane. So when you go from A to B, your normal is maintained, the pressing force is maintained, and so your friction will be always maintained, mu k into N is maintained here, F. And therefore, if I ask you what is the work done by kinetic friction in this A to B, what will you answer? Tell me, what will you answer?
Mu F into L1 plus L2 plus pi R by 2.
Minus mu F into
Okay, minus mu F
L1 plus pi
pi
by
R by
2
2
R.
plus L2.
Right. So you can see it's pretty easy. If you know that a force is a constant conventional force, I just need to write the force and multiply with the length of the path, whatever it is, and we are done. Okay. A third variety of question that we come across in friction is this very, very important. Again, let me show you. So this is called, so you might have seen the skating, what do you call it? Where skaters do the moment. It is having some name, but I don't remember the name. So I'll draw a simple. Okay. So bottom is rough and the length is L. The height is H. So you release something from height H. It falls along the wall. Okay. I can tilt. Okay. What I'm doing. This is not good. And now this question can be solved with a proper numerical value. But I'm trying to generalize it, and we have a tiny block. So the inclined part are smooth, but the base is rough. Ignore the dimension of the block. The mass is M. You have to find the position at which the block will stop from the left end. Okay, so what is the question? Well, let me give you some number. Maybe that number will help you in solving that. So and L is 1 meter. All right. So question is where the block will stop. Where the block will stop.
So this is the mass given.
Mass is given, but mass doesn't matter. I think. But let's take mass. Okay. Two things. I don't think mass should matter, but anyway, let's.
Yes, sir. I
Yes.
don't think that matter.
So you're not supposed to, find the energy lost in every time you're crossing. What you can do is that you can just find what is the total energy available. So what is the energy available? I think I should go to the next page. I don't have space left.
Sir, I was
So
getting the answer as 10 meters only,
yeah,
which
So
is not
10
possible.
meters, it will 10 means what? 1, 2, 3, 4, 5, 6. So 10 means it is coming back, right? Or it will land
Yeah.
at B or A.
So not sure.
It will go from
So mathematically, I was getting 10 meters.
yeah. So it means it will you start from A. So after 1 meter you are a bit. After 2 meter you are at A, right? 10 minutes will again come back to A itself. If it is even number, it's back to A, right?
Yes, sir.
So the answer is simple. You have to find the energy lost. So total energy available is mgh and divided by the frictional force, because we know this is equal to Fk mu mg into some distance, or you can travel whatever you can, how much I need to travel in order to consume all energy. That is the whole idea. To consume all energy, how much I should travel. So let's say you travel S is what? The length of the path, right?
Yes.
So it turns out to be h by mu, that's it. And h by mu is how much? 2 by 0.2, which is 10, right?
Yes.
And because it is 10 meters, so we know that the length of the base is only 1 meter. So in order to consume all energy, you have to travel a lot and eventually you will settle down at A itself, isn't it?
Yes.
So to make it more interesting, let me make it. Let me make the base length as 1.5 meter. That's will be interesting. So now 10 meter means we have 1.5 meter track. So how many times you can consume completely? 1.5 into 6 times, right?
Yes.
So 1.5 into 6 is 9. So 9 meter will end up where?
At
1,
A.
2, 3, 4, 5, 6. B. 9 meter is a B, right? If 9 is B, then we have to travel 9 and how much extra? Half. So you will travel half from this position, half meter, which is like 1/3, isn't it? So the block
Sir,
will
after 9, you have
eventually
to travel 1 meter no? To complete
yeah,
the
1 meter I have to travel. Correct. So it will end up at this point, right? Sorry.
Yes.
So 1 meter means it will yeah, that's okay, that's fine. The block will end here, right?
Yes, sir.
And this is L by 3, L by 3. So 1 meter. So 3 by 3. So this is where you will stop eventually. So these kind of questions will come, and that is the use of kinetic friction work. You can simply consume the energy by traveling to and fro till you consume all energy, and just check the length, how much length you need to travel to consume all energy. And the answer is very interesting. It is simply h by mu, right?
Yes, sir.
So that will give you the whole idea that how much you need to travel, and then you can check the base length and then guess that where you will eventually stop. So this is very uh, old and very powerful question. We used to solve in our time also. And we will also come across question like this very often. So kinetic friction is a magical, I mean, you will come across question of kinetic friction in a variety of ways. Or you could have written the same thing like this. Alternatively, you could have written the energy minus work done by kinetic friction is eventually making the all energy zero. So this is how you can rewrite, and from there you can get the answer. And because the inclined plane is frictionless, so we need not to worry about the normal reaction. correct?
Yes, sir.
And there is one more interesting thing which will come across, and that is even more useful and important to remember. So we have a track and you are supposed to assume there is no corner, so it is a smooth transition. Okay, so we are not assuming any loss of energy. I'm taking this as 37 degree, and this mu is 0.1, but this mu is 0.2. And I have a block of negligible dimension. So I have a block of negligible dimension. And the height is, let's say, 2 meters. Okay. Ignore the size of block. Assume the joint of plane with horizontal seamless Okay, so now if I call this is A, this is B, and eventually the block, let's say, come to rest at C after traveling this is X. The question is find X. So can we find X?
Yes, sir.
So try to do this. Solve it using the work energy theorem. That's easy. Okay, done, Siddharth? See, whenever you want
So-
to solve question, you should first do the ABD, the free body diagram, just to see that what are the forces. You can see here we have normal, we have gravity, and we have friction, correct? But coming to
Yes.
the base, we will have a different normal, and mg will remain same, of course, but the friction value will change because the n will change. So we should write the equation for two parts separately. And here will be mu n2, mu2 n2, let's call mu2, mu, and this part will be mu1 n1 mg. Okay. So if you look at the forces, we have three forces for the both the plane. And you can also realize one thing, that the normal direction is not doing work at all. So no matter whether you're on the inclined plane or on the horizontal plane, normal is doing zero work, right? So for the entire journey, do we need to write a work done of n1 n2? The
No,
answer
sir.
is no need to write. But you should write the work done of friction for the top part and bottom part. And it is always negative. So what we can write? Minus mu1 n1 into this length. I have to actually calculate using the a sine
So
theta
it will
is
be
h.
6/5.
Yeah, so it is 2 by 3 by 5, right? Huh? Yeah, a sine 37 is h. So 3 by 5. So it is 10 by 3, right?
Oh, okay, sir.
Yeah.
I made a mistake here. That is.
So mu1 n1 into s. I'll just write like this. And when you're at the bottom friction, we change the value to mu2 into x. Now gravity will do work only when you come down. So for gravitational work, the simple thumb rule is just check how much you have come down vertically. And if you're coming down, the gravity will support you, so it's positive work. And there is nothing else left. So this is it. And since you start from rest and you come to rest, the changing kinetic energy here will be zero. You start with zero, you end with zero. And therefore, the mu2 n2 x is mgh minus mu1 n1 s. And then you can see that you can get x equals to, okay, you can, if you want to put value right away, you can put right away. So mu2 is 0.2, n2 is mg x. mgh minus mu1 is 0.1, n1 is mg cos theta actually. All right, into s, which is h by sin. So mg gets cancelled. That's why I was not substituting the value. And you can realize that this is 0.2x is h minus 0.1 h by tan theta. So very interesting. H is common. So 1 minus 0.1 by, and tan theta is 3 by 4, right? 3 by 4.
Yes, sir.
Okay, so this is h by 3 into 2.6 upon 0.2 is x. So x comes out to be 13 h by 3, 13 by 3 into 2, which is 26 by 3 Newton. So fair enough. But what I wanted to actually tell you is something even more interesting. If you have understood this part, then I can go to the next concept. This is clear?
Yes, sir.
So let me show you something even more interesting feature of kinetic friction. Kinetic friction is something really amazing. Like throughout this chapter, the only thing which troubles most of the student is kinetic friction. And if you can realize, it is amazing actually. I mean, it is actually amazing. So this comes through a problem called the Hill problem. And Hill problem is the most famous problem in work energy power. So it can become Hill means any curvy linear path. Okay. So this is from I Rodop. You can just see this. You will see this picture everywhere in most of the textbook. They give this problem. So the idea is you simply choose a curvilinear track and the vertical height is small h, that's called, and this is L. L is from here onwards, from here to here. Okay. And try to understand what is going to happen here. Question is, I need to put some language also. A block is at the bottommost point. We are ignoring the dimensional block. So a block, sorry, no. A block of massing is pulled up the hill slowly by a tangential force, by an external agent, by an external agent direction of force, direction of external force by agent is always parallel to the path find the minimum work done by agent to take the block to the top of the hill. So, okay, it goes like this. You have a block, and as you climb, and what is interesting that the shape is not known. What is the exact shape? The information that one should be focusing here is the word slowly and the direction of force, which is parallel. So when I say the word slowly, it means the block should not accelerate at any point, which means the tangential acceleration of the block is always zero, as well as the centripetal is also zero, because it's a curvilinear track, so it could have both the acceleration. So slowly we'll make sure that we are not actually interested in the acceleration part. Okay. So the word slowly means zero acceleration whatsoever. So zero acceleration means neither centripetal nor tangential, or the total acceleration is zero. So that is the whole idea. So question is, if there is no acceleration, then how to find the work? Now, if you have not solved question like this before, you won't be able to think much of it. So for the first time, you deserve to see the solution. If you want to solve, if you want to try based on this idea, you may try. I mean, if you can get some clue from here, you may try. Otherwise, I can solve right away. So what do you want? You want to try, Siddhant?
Yes, sir. Give me 3-4 minutes. I'll
Yeah,
try.
yeah. Think about 4 minutes. Fine. Take your time. Okay, so let me give you the process through which we can derive the answer. So definitely, it's a rough surface. Actually, okay, I failed to mention that it's a rough surface. Okay. So because of the rough surface, if you are at some random location, let me put it here. So let's say you are here somewhere, and you're moving slowly upward. So what are the ABD? What will be the ABD of this block? So I can directly draw a force like this. Like this. I'm just resolving the component as well. And down the plane, there are two forces. One is gravity, another is. So this is your normal. And let's assume the tangent to be making an angle theta. Yeah, we have to do this angle thing on our own. Other component is mg sine theta, and the other is mu n, right? So to move it slowly, and by applying a parallel force, we must apply force in this direction at this point. And this force will balance out the all the other force acting on the block along the tangent. So can we say the F value must be equals to mg sine theta plus mu n, which is mu mg cos theta? Can we write?
Yes.
So this is coming from the fact that AT is 0. And therefore the F must be this value. And because it's a variable force, so we must write the elementary work dW. So that is the way to approach. So dW equals to, so you move by ds, elementary length ds, so the work will comes F ds. And because the angle is 0, so it is F ds cos 0, which is F ds itself. So here comes the interesting part. So you have to write like this, which is mg and further you have to think this way, that ds sine and ds cos will become dx and dy. So that is the beauty, the mg and the ds sine theta will become dy and mu mg dx. So do you realize this part? The answer has nothing to do with the path. Of course, what it depends is on the x displacement and the y displacement. What is also interesting to realize that work done by gravity depends on the y, and work done by friction only depending on this case on x component or x displacement. Of course, mu mg is not coming out of nowhere. So it is as good as if a block is moving along a x direction, where normal is mg. And so the answer is coming that way. So in future, whenever it comes to solving the question of work done by kinetic friction, you can simply add mu mg into x displacement, provided the normal is only equals to mg cos theta. I mean, if n is not mg cos theta, we cannot apply. And now this is pretty easy to integrate. So the total work is how much? So don't worry, this is a very famous answer. And one should be aware of these ways of solving. So the first term will become 0 to h, second is. So you can see the answer is mgh. And that's why this is very crucial problem. That the ds way of writing, see, you write elementary work. So that is your learning from here. If you understand that I need to write elementary work for variable force, And then you have to think about, can be simplified further. So ds cos, ds sin is always a meaningful thing in physics. You will always come across things like this very often, not only in this chapter, but also in electrostatics, gravitation, uh, electromagnetism, magnetism. At various places, this kind of question are very commonplace. It is everywhere. So di is ds sin theta, and you can clearly see. So of course, we are not born with this thinking. We have to learn first. We have to see at least once, and then when you see the next time, then you will, this will act as a concept for you. So when you are solving the same question next time, then definitely it will be very easy for you. And what we can draw a conclusion about frictional work is this, that work done by kinetic friction. If you write only work done by kinetic friction, you can see it's minus mu n ds, which is minus mu mg cos theta ds. Now I can replace minus mu mg dx, because that's the ds cos theta meaning, and therefore oh, I need to integrate first. And that's why you can see the work done by kinetic friction is actually negative of mg. That's very interesting. But the slowly is the case. Like this is the derivation only if the motion is happening very slow. Okay. So based on this idea, you will come across a variety of question. Like what? So let me show you one question. Let's say we have a hemispherical or semicircular cylinder. Doesn't matter how you think about it. So let's call this as semicircular cylinder. If it is my semicircular cylinder, which is a fixed object, let's say this is fixed. And there's a tiny object of mass m, which is like kind of hanging here. So what is happening here? A person is pulling this mass, okay, right over the semicircular cylinder of radius r very slowly. So slowly means the mass which is getting pulled will never accelerate, and it is kept on a rough surface. So how much work is required to pull the object till here? I'm not putting the complete statement of the problem, but this is the gist of the problem. So you can say, what is the work done by F in pulling the mass slowly from A to B? So what will be the answer? So it is as good as a hill problem, right? Because if you look carefully, the tension is always parallel tangential, isn't it?
Yes,
And
sir.
and it is the tension which is pulling the mass, and tension is equals to F. So in a way, it is the same question as the previous question. So what should be the answer? What will be the work done? So it is always you have to work against the gravity and against the friction, right? So against the gravity, how much you have to add energy? Gravity will do positive work or negative work.
Negative.
So negative means gravity will take away the energy. So that energy should come from you, right? So how much energy you have to give? Yeah. So what do you think? What should be the answer? How to write the answer? Tell me.
Sir, MGH plus
mgh plus mu mgl.
mu
What is
mg
h here?
pi r
What
by
is h here? What is h here?
H is R.
And l is
Mgr plus mu mg pi r by 2.
mu mg r only, na? Why pi r?
Sorry, R.
See, mu mg pi r by 2 is answer when the friction force is constant. But here friction is
Yes,
not constant, right? Because it is mu and n is variable here.
yes,
So that cannot be the answer. So here the answer is mu mg into horizontal displacement. You have to always check this answer. So try solving this question twice, 2 times, 3 times. Try to realize. And these are the questions which you should remember as a theory in order to solve some of other challenging problems. So always you have to remember that these are the fundamentals based on which you have to solve the other questions. So although these are problems, but these are theoretical problems. Like these are questions through which we get our theory clear. The theory required to solve numericals. Okay.
yes, sir.
So your answer is it's very interesting. MGR 1 plus 1. And in fact, this is a challenging problem. But if you know this theory, then it's a one-line problem. So you have to make sure that okay, you understand the difference when to apply what, because it is easy to get confused between the two relations. So you have to create your own strategies. Okay, in this situation, I have to be careful that this will not be applied. Because friction is not a constant force here. So when we take the path length, potential force when it is constant, right?
Yes, sir.
So here what is happening is the variable answer is kind of reducing that answer to mu mgr. So you're pulling the object slowly, which means the force is tangential, it is slow. So this is always the answer. Whenever in doubt, solve from the scratch, get the answer. Okay. So these are the work done by variable force, which one should be aware of. The other category is called chain problems. And then there are many more categories. So we have to do a lot of things in a variable force. So next section we can also dedicate half for the, in fact, the entire lecture will be for the variable force, and spring force will come predominantly in that chapter, which and we will be solving a lot of question of spring based problem. Okay. So as of now, I'll stop it here. And I have shared your sheet with you guys, right? Just let me see what we can solve now. Mhm. Okay. So in the exercise 1, you can of course solve section A completely.